Hello, and welcome to our presentation on the paper Evaluating Transfer Learning Methods on Real-World Data Streams, a case study in financial fraud detection. This work was done as a collaboration between FIDSAI and the University of Porto, and was then published in the ECML PKDD 2025. Let me start by framing our problem. In machine learning, we use data to train machine learning models, and we know that the predictive performance of these models is closely tied to the size and the quality of the datasets that we use to train it. The problem is that sometimes we have very limited data available, or even no data at all. A promising technique to solve this problem is to use transfer learning. The idea here is to leverage the knowledge from one or more source domains to improve performance on a target domain that has limited data. When this problem is studied in academia, researchers typically divide it into different subproblems or paradigms. Their main differences relates to how much target domain data we have available at training time to develop our models. For example, in domain generalization, we assume that there is no data from the target domain available, so we build models using source domain data that can generalize well to any previously unseen domain. In domain adaptation, we have some target domain data available, but usually a much smaller volume than the source domain data. This data is assumed to be unlabeled in the unsupervised case, and at least partially labeled in the supervised case. In multi-domain learning, we have a significant amount of labeled data from all domains, but we still want to share the knowledge to improve performance across the board. To evaluate and compare these methods, researchers often use popular transfer learning benchmark datasets such as PACS and Office 31, which contain data collected from different domains. To design their experiments, they select the source and the target domain, sample some instances, and optionally conceal their labels to match their data availability assumptions. So, this could be an experimental setup to train and evaluate an unsupervised domain adaptation method. However, in practice, it is often the case that data from new domains is gradually collected and labeled over time. This means that the assumptions regarding data availability cannot be static, but should account for this dynamic nature. For example, consider global services such as a streaming platform expanding into a new geography. They may initially lack user data from this new market, so they can only rely on historical data from other geographies to build their recommender systems. However, over time, as they collect more data and labels specific to the new domain, they can use it to fine-tune their solution to improve the quality of their recommendations. In these situations, the conditions of data availability are not permanent, because data from the various domains is progressively collected and labeled over time. This means that the typical assumptions of the four scenarios of transfer learning that we saw before are still valid, but at different points in time, gradually evolving from one stage to the next. So, while an academia is studying these scenarios as separate problems, the dynamic industry scenario with the continuum of stages is sometimes overlooked. In order to properly study this problem, we need to create a protocol to provide us a testing ground for different methods, evaluated under different settings. Similar to the other transfer learning benchmarks, the tool should be able to represent data from different domains. On top of that, it should also simulate the progressive arrival of data and labels over time, and evaluate the methods under these different conditions. And finally, we should be able to effectively run multiple variants of the experiments to make the results more robust and representative of many real-world industry problems. To achieve this, we propose the following evaluation framework. It consists of three main components that work as a pipeline to prepare the training and evaluation of the transfer learning methods. Starting with the domain sampler, it creates multiple domains from a given dataset. This allows us to simulate settings with many domains even when the few datasets are available. It also lets us introduce variability and potentially highlight differences between domains. To sample each domain, we select an anchor point, compute the distances from it to every other instance, and then sample the instances with probability decreasing as the distance to the anchor point grows. Next, the transformations apply controlled changes to the data to mimic realistic shifts over time and across domains. This allows us to simulate many variations of the experiments, such that we can study the statistical significance of the results and learn more generally applicable patterns. We provide examples in the paper of transformations designed for financial data. Lastly, the scheduler simulates the gradual arrival of both data and labels over time. It decides when the target domain data starts to arrive, how long the labels are delayed, and the length of each test period. Based on that, it generates a sequence of data splits that grows over time. With those splits, the scheduler orchestrates the training and evaluation of the transfer learning methods, making sure each one is only run when the right data conditions are met. This means that the only domain generalization methods are trained and evaluated on the first test split, as no other target domain data is available yet. Then, once we have unlabeled target domain data, the unsupervised domain adaptation methods are trained and tested as well. And finally, once we have target domain labels, all methods can be included. In the end, this allows us to systematically study how different transfer learning methods perform under a whole spectrum of data availability conditions. These insights can then guide decisions about when and how to deploy models in real-world settings. To showcase the capabilities of our evaluation framework, we conducted a case study on the problem of financial fraud detection. We ran our experiments on two sets of data. The acquirers is a real-world proprietary dataset containing payments from 4 different financial institutions. Meanwhile, BAF is a publicly available synthetic dataset consisting of account opening applications. We should note that the experiments that we ran on each dataset were independent, and we did not do any transfer learning from acquirers to BAF or vice versa. Regarding transfer learning methods, we implemented some representative state-of-the-art methods from each of the 4 types of problems that we discussed, as well as some simple baselines. Our goal here was not to conduct an exhaustive benchmark, but rather to show how our framework enables the comparison of diverse transfer learning methods. Before we analyze the results, let me first explain these plots. This is a recolored version of Figure 5 from the paper, where we can see the predictive performance of various methods over time, with the number of weeks counted from the start of the target domain. We ran a total of 64 experiments, and we see different aggregations on each panel. On the left, the solid lines represent the median recall for each model over time, while the shaded regions represent the interquartile range. On the right, each dot represents the average recall per method per time split, while the brackets are grouping methods whose differences are not statistically significant according to paired t-tests controlling for 1% false discovery rate. Regarding the results themselves, we see that domain generalization and unsupervised domain adaptation methods, which do not use any target domain labels to train, are consistently worse than the rest, which may suggest a significant domain shift. Meanwhile, multi-domain learning and classical machine learning methods are immediately better and continue to improve over time, showing the added value of increasing the volume of labeled target domain data. Supervised domain adaptation methods initially seem to follow the same trend, but plateau earlier. And finally, we highlight that in general, the differences within each group of methods are less significant than across groups. In an industry setting, these results would indicate that labeling efforts should be prioritized, as we see that it leads to significantly better predictive performance. As for the results on BAF, we see a completely different picture. Here, the domain generalization and the unsupervised domain adaptation methods show a strong and stable predictive performance. Multi-domain learning and classical machine learning methods start by having a weaker performance, but improve over time, eventually matching the performance of the previous group, and supervised domain adaptation methods are consistently surpassed by the other methods. Similar to the acquirers, each group of methods behaves somewhat consistently. These results may be due to the different domains being actually sampled from a single dataset, BAF in this case, so it is possible that the domain sampler and the transformations that we applied were not enough to induce significant changes across the domains. To conclude, what are the key takeaways from this presentation? In this work, we tackle the problem of how to effectively evaluate transfer learning methods in settings where data is collected over time. To address this, we propose an evaluation framework comprised of a domain sampler, transformations, and a scheduler to systematically simulate many scenarios of gradual arrival of data. We showcase the framework on the domain of financial fraud detection, showing examples of the type of analysis it can support. If you'd like to know more about our work, I invite you to read the preprint version of the paper, available on Archive, and to check our GitHub repository with the open source implementation of our framework. Thank you very much.